Another draft physics video presentation. So some good news. Baldy Cats has accepted my invitation to a debate. As awkward as that whole process was. And so on July 29th, we will do the thing. And so I have plenty of time to prepare a totally indestructible argument and all that stuff. There's always lots of subtleties about light, and so I propose that the general subject will be, the idea of ray versus wave theory. It doesn't really have to be particles. It just has to be the idea that light is a confined thing traveling through space. I suppose I could illustrate it as being something like this. Yeah, it's like a piece of paper flying through space. It has a very large polarization, very little width, what I would say to really understand it is I probably should just draw it on here on this piece of paper, that the photon really is this. Okay, it's, oh, look at that, you can't see it at all. There we go. Okay, that it's little bits, in sequence, flying in this container. Okay, so the container isn't full of photon. It's just this is a container for the photon, and the photon's little bits of quanta are out of alignment. Okay, but they're all going parallel in a direction, and so I'd argue that's okay. So when somebody says photon, that's what you should be thinking, right? Not what this, wavy stuff, but just little bits of energy moving parallel, okay, through space. And that a whole bunch of them can be all piled in there. Zillions and zillions. Can be occupying essentially the same blob of space. You can fit lots of pieces of paper at lots of different angles. Anyway. Just the whole thing about what light is and what defines how much of something is a photon, how many little lumps in the wave, all those kind of conversations that never take place. So all of those, I would think, would be part of the conversation. We'll see how far we get. Just in analyzing the two-slit, there's just so many little nuances and details. So I thought I'd go through some of those just partly for my own benefit, in making sure I have all these things sewed up so there can be no rational dispute about any of these facts and the premises, the axioms, the truths that underlie understanding the experiment. So some of this will be redundant. Sorry about that. I'll get rid of me there because I'm not helping you see the pattern. So I've used this image before just because it's a very good image, just illustrates the difference between the single slit on top and the double slit on the bottom. That obviously the double slit is a composite of more than one pattern, and that all needs to be explained. And it has, it's not just that it's two patterns, but it's two patterns doing a similar thing, it has very similar properties to the two patterns. And so the first simple argument is, again, I'll just reiterate the argument from how you display the thing properly. So even if you have a wave theory and think there's interference in space, the interference all happens pretty quickly because of the frequency. I mean, the size of your waves are incredibly close together, so I can't draw them anywhere near as close together as they are. And so all of this, even if this interference was to take place between two waves, the idea would be is that it would happen less than a millimeter from the surface. They'd already have done all their interfering, all that they need to do to create the pattern. So the simple argument is that anybody can understand, I think, is that if you display the pattern on a flat screen, you're going to be deceived because these angles or views, you can understand that as you go further out, like say if I was to put some object in here, that if I displayed that object's shadow, the object's shadow would get bigger and bigger the further out I go. So straight, everything is, you get the right size, and every angle I turn, the size starts getting very, very distorted. And you can see that in the pattern. And in other displays of the slit patterns, you'll notice this thing where as you go further away, the dark spots get bigger and bigger and bigger, and the light spots are getting smaller and smaller and smaller. It's because there's fewer and fewer photons, and that's why they're getting smaller, but the dark spots are in fact getting larger because everything's getting stretched. So you can understand that in displaying it, you're cheating the reality, because it will display this block very, very different, very big, and in proportion to this one. And so you'll get a completely artificial view. Now the complexity is, see, there's all these little subtle complexities. If I were to propose that you just put it on a, equidistant circle, now that clearly doesn't hurt your experiment any. So you just find the center of the experiment, you just go an equidistant, and you just make an arc, and you now will get correct proportions. Okay, now you understand that anything that's made, they'll all be the right size. So this same block here will be the same size as a block here. Everything will be proportional. And what you'll also realize is that, oh yeah, there's not an infinite pattern. There's not pattern forever. That the fact is that all the infinities will be here. Any idea of sending stuff further and further and further and further on a flat screen, all will have to go through the one single block, and there won't be a bunch of pattern. There'll just be a block that will go for infinity. Okay, the block will be infinite, not the pattern. The pattern won't keep going. Just the last block will be so gigantic that it'll go forever, so to speak. So this really does make that understandable. So it's understandable that if you're going to do this clinically, if you're going to do this precisely and accurately, this is the only way to say what does the pattern look like, is to put it on this arc. Now the problem is if you're a viewer here, okay, I probably can't, yeah, you can see that, excellent. You're going to have a different view of that arc than if you're a viewer here. And so how far you are away from that arc, if you were to look at the screen that had this perfect arc, if I made the arc the screen that was a perfect half circle, the problem would be is you'd get a lot of distortion depending on how far away you are looking at that arc. So that's where that sort of breaks down. Is the same thing will happen if you don't account for distance, that how far away you're looking. The further away you would look at it, the smaller and smaller the things on this side would get. So you wouldn't even see those anymore. They'd be so infinitesimally small, and the big one and the middle one would get bigger. So you have to compensate and say, okay, you take into account the distance you're viewing from. So for viewing purposes, you would just use a circle that's more, that's bigger, that has to do with you being, okay, one of the radiuses. So you have a combined arc. So that's why movie screens aren't this shape. Okay, it's because they have to account for how the viewer is looking at it. The distance the viewer is from the screen is part of the calculation for figuring out what this arc should be. So I just want to make it clear that this is the clinical drawing. Like if you're looking at it from the top down, this will give you the accurate thing. Where this is what you got to do if you're going to actually view the pattern on a screen. The screen has to be changed to account for your focal length of your point of view. So it's just one of these little technicalities, and so they're all part of this argument. Okay, the other interesting, so the Stephen Bro guy did make a video. I understand now what he was doing. Okay, he just took the single slit experiment with a known width. Little pause time. Alright, should be back. Ugh. Yeah, looks like it. Alright, so let's just say this was, see these numbers are kind of important. You say 0.1 millimeter, you know, that's really 100 micrometers, which would be essentially 2,000, you know, at 500 nanometers, it would be essentially 2,000 wavelengths. So it's a pretty big distance, even though it seems like a really small distance to photons. Making it out of photons, it's a lot of photons. So anyway, so Stephen had, well, you know, Stephen Shitstein, you know, let's call him by his real name, you know, is making these assertions. So what he did was take a double slit and a single slit where the impediment's supposed to be the same size as this opening, okay, whatever it was, and displayed them, okay, and says, okay, they're not the same. So he just measured from a distance, put one in, then did the other one, same distance, and said the two are a different size. Well, you can sort of understand why they might be a different size, is because more photons. You can't say it's twice as many photons. Obviously you have twice the opportunity to create photons, right? So you have twice as much opening. That means you're going to get 2x amount of light. Now I'd say it's something less than 2x, because even though a laser beam is pretty consistent, it's still weaker, okay? There's still less of it at the outside and more of it in the middle, right? So you can sort of get that, the beam. And so you're going with the lesser amount of lights going through the slits, but you're blocking with the impediment, you know, the strongest light. But it's still close to 2x. So it's twice as much light that's going through photons, pieces. And we also know that this is, you know, they will concede, although they have no rational explanation for it, that the effect is squared. So you're really getting 4 times as much light that actually, you know, pieces, whatever, brightness. So for every bit of opening you add, you're adding a multiple of that amount of light. So it's not just that simple as just twice as much light. It's twice as much plus the fact that it ends up, because of the way the patterns, where the light ends up going, that it'll be 4 times brighter in those locations. Well, anyway, so obviously you should expect some difference between the single slit and the double slit, in the sense that, yeah, they might be a little different in size, but the size just has to do with how much of the space they're consuming. So as you can see from the fringes, so if you look at the fringes there, they're a set node size. So you see where there's 5 little dots, okay, you probably can see that on either side. There's 11 in the middle, which sort of makes sense. So you know the nodes are 5-ish, 5 little dots in size. And you can see that those nodes are much larger than the dark space. So the spots that end up being bright are not proportional to the size that they end up dark. So the dark spots are smaller than the light spots. Now what you're really doing is saying this is where you have full wavelength constructive, and this is where you have full wavelength constructive, and this is where you have full wavelength destructive. Okay, so if you understand, well, I should do that in a different color if I have a different color available. So those distances have to be the same. Okay, the distances from the centers would obviously have to be the same. Okay, so where the centers are is the same distance, but what you're going to see won't reflect that, because, you know, for reasons they state a reason, but I'm just saying the idea is that this is going from gradually on to gradually off, and then gradually on to gradually off. And the fact is that we're seeing that unevenly. Okay, we're seeing more of the on than we are seeing the more of the off. So that's why the bright spots end up going bigger, okay, than the dark spots. Now in the image it's going to look different. It's going to look like the dark spots are getting bigger, But that's the part being created by the distortion. That's the part being created because your view is on a flat screen and you're stretching, okay, everything, the dark spots and the light spots. And you're not only stretching the light spots, but as I pointed out in the other video, as you stretch the light spots, you make them less visible because now the photons are further apart and you're getting less and less reflections, and your eye can't see, they're too dim for you to get enough photons to see the real pattern size anymore. So the pattern's getting fainter as you go further away, which makes the dark spots look like they're getting bigger when they're not really getting any bigger. So it's center to center that you have to measure. Measuring this size doesn't mean too much, because the fact that the one pattern was bigger doesn't mean that it just means that the dark was maybe smaller. Okay, so the darks were small. I should do that in green. Alright, the darks were smaller here, okay, and the darks were bigger here. And so that's all you're seeing, is that the patterns really are the same size from center to center. Alright, it's just that because you sent more light, you saw more in this one than you saw in this one. Okay, you just didn't see its full size because you didn't send enough photons. You just sent twice as many photons to make the other pattern. And so, you know, they'll call these rationalizations or excuses or some other kind of word, but no, it's just part of the details. There's details, you know, and they're not as simple as we'd like them to be. So one problem I noticed, you know, that's a little, you know, you look at the pattern, you say, okay, so there's 11 things in that middle. So the two patterns, you know, I could compare them. Let's see, it's the best way to draw it. Just thinking for a moment on the best way to draw it, right? Okay, so the argument is that these are just point sources, and there's always going to be vectors. Now they draw vectors for the two slit, they use these wave centers, but they actually don't, because their math is just about this distance. So when they have their distance, their number that's going to decide how many wavelengths are creating the pattern, they're using this distance. They're not using the centers of the waves. So they can draw it one way, and their math is doing something entirely different. Their math is doing this and this distance. Okay, their drawing is doing this distance and this distance. So their math, their math and their drawing don't even match. And of course, as stated, there's no way to use two waves and create the double slit pattern. Two waves can't create both patterns. So wave theory just doesn't work. Their illustration doesn't work, and clearly their math is deceptive because their math isn't, there's no wave coming off this corner, and that's where they'd have to put their wave here and here when they draw it to be consistent with what they're using as their math for the center of the wave. So clearly their math is a deception. It's not what they say it is. Alright, and so the trick is, so I'll just draw it going this way just to not mess up this for whatever reason. I might have use for this. So just let's pretend these are the point sources, and you're really saying they're equidistant. And I won't do that perfectly, so there. Okay, so you say the center, there should be one of those lumps of light. Okay, so that's kind of, okay, yeah, you get that. But in the single slit, you can clearly see the lump is much bigger than that. So that doesn't account for it. But the trick is, like say if I did have I think I have enough room down here. So let's just compare that to the open slit. Now the problem is, see, when you have the difference between the impediment and the slit, the difference is that you're getting all this light that goes straight through. So when the single slit pattern is made, a bunch of light goes straight through and hits this center area. You know, and what is really behind that is the fact that there's really 3 nodes. Okay, so you have, yeah, you have this little one, and then you have one here, and then you have one here. And what's really happening is this center light is so bright that it's wiping out this dark and this dark. And that's what's creating that big center, is the fact that that extra light that goes straight through is wiping out the dark that should be here and the dark that should be here. And so this is really 3 nodes, okay, technically, you could argue. Now, I haven't done all of the measurements to see if that is possible, but I'm just saying it's a possible explanation. I think it works for why the single slit creates this bigger node in the middle. And then when you do the double slit, the little tiny things, right? See, there's 11 little lumps in that middle section. So obviously there is one little one in the center, and then there's 5 going this way and 5 going this way. So this center one is the same size as these. So there is no 3 times bigger thing happening. And the reason why it's not happening is because when the impediment's in the way, there's no light going straight through there. Instead, the light goes straight through here and here, which can't make much difference, right? So, you know, as an argument, you're almost saying, well, this is only a millimeter across, you know, maybe a little bit more, a millimeter straight across, but it's a little bit spread. You'd still say it should have wiped this dark space out. So, you know, it's a difficult question to, you know, I still say this is part of the answer, is this straight, you know, the most intense light is wiping it out. But, you know, there's logical reasons to question, so I have to ponder that question some more. So it's one of the open questions, is why in the single slit there's the big giant center thing, and in the double slit, okay, the secondary pattern or the primary pattern, however you want to look at it, the little pattern. The big pattern is doing this, okay, so you can see that quite clearly, that that's doing exactly the same thing. The envelope pattern, as it's called on the double slit, is doing exactly what the single slit's doing. It's making the big giant thing. But somehow the same vector kind of view, you know, where you're basically saying these 2 lines converge, okay, on a point. And the argument being made is for the little pattern, it's the conversion of these 2 lines that are deciding the point. And why would there be a difference between this creating a big blob and this creating a node, let's say a big node? That's maybe the language I have to use. A big node, you know, versus these regular size nodes. But in the double slit, these surfaces that I say are creating the pattern, the small pattern, don't create a big node. And so, yeah, that's, like I said, I have an argument, but I just don't know if it's a good enough argument. So we'll have to work on that one. So we have some 2 weeks to do that. 3 weeks. Anyway, yeah. So I hope you got my point, that this is how it comes out, and then the double slit, it just comes out, they're all even. Okay, so the center one, let's say there was 5, and this is your center one. The center one is the same size as all the others. That's the argument. Why that difference? All right, so moving on to the more the better stuff, the stuff that actually proves the argument. So I think it can be understood that there's no infinite pattern, that there's only a certain number of locations on the surface that can produce an angle difference, a wavelength difference, a path length difference. So you only have a certain number of path length differences in this arc. And that's the way it should always have been understood. They've been using a sine theta, an angle difference. See, they use the angle to decide the path length difference. So by establishing the difference between, to get to one location, this angle will be a little bit different than this angle. So they're using the difference in these angles to equate to the difference in a length in a line. When I'd say the obvious thing to do is just to point out the two lines are going to be a different length, and the two lines essentially have notches on them, and that they have a different number of notches, and the notches will line up in some locations and they won't line up in other locations. And it's sort of that simple. And then you can just do the string argument where you move the string around and on this arc, and you can just see that if you put the same notches on both proportional, that there'll be places where the notch hits the notch hits the notch hitch, and that's all you have. So the pattern is a limited pattern. If you put it on an arc, all the bits are the same size, all the nodes would be exactly the same size, and you'd see that every pattern created, so every change I make to the slit size will just make a change in how many wavelength differences these angles can produce. So the wider I make it, the more angle differences I can create. So the smaller the little nodes get, the more nodes you can have, and the bigger the distance, the shorter the distance, the bigger the angle changes and the bigger the on-offs become. And so you're just really saying where, that's all you're just stacking nodes of where they're in phase. So where the two lines, where the rulers match, the little notches match on, if you were to use two rulers, you could just match where one says 1 inch, the other one says 2 inches, one says 2 inches, the other one says 3 inches, one says, you're just measuring where the distances are the same, and that tells you where you have where the center of the node will be. So remember, it's just about where the center is and where the center of the off is. You can't go by the size of the light, because the light spreads into the dark regions. And so the whole other subject is, why does that happen? So there's two reasons it can be argued. I guess I should finish this node thing. So you can sort of understand that there's with 4 sources, you have 4 varieties of lines you can create. You can match. So let me just erase that. So I can go from this point and I can go to some point on the board, and then I have the difference between these 2 points, and I have the difference between these 2 points, and I have the difference between these 2 points. And when all 4 of those are in phase, you get a hard bright. But the idea is they're really just stacked on top of each other. So you're stacking this distance, which would be a big blob, okay, a big notch, okay, and then you got a little bigger distance, and so that's a smaller notch, and that'll be on top of that one. And then you got this distance between this one. Yeah, we got this one, that one, and then this one. Yeah, and then the last one is on top of that. And it's only when all 3 of these line up that you get a bright photon. And so when you go across, they sort of are matched to each other. So the big one is halfway on that one, and the little one is always on top of that one, the center of that one. And so when they line up, that's where you get a photon. Alright, so the other subject was, there's 2 arguments to be made here about the phase, and why why are they shaped the way they are. When the pattern stretches, and obviously that's sort of what you're saying, is it stretches. Why does it look like this? Why does it have this shape when the light hits the board? And why are the little blobs, in this case especially, they're very round in the fringes. They're very round. And so these are questions they don't answer, because it really just doesn't fit this idea of the wave. It's not proportional to what the wave would produce in terms of an on-off pattern, gradually going on, gradually going off. It's not symmetrical to that notion. And the argument is that you do have these explicit points where you're on phase and then you're a little off phase. And so understanding what the phase is, I guess, is part of what I should just show. So if you understood the wave theory, okay, you could argue, their waves have two waves, but the magnetic one really isn't doing anything. You could think of each one of these as just a node, right? It doesn't matter whether you think this is the node or you think the peak is the node, or it doesn't matter. But you can think of it just as nodes, right? So you can think of it as just points, quanta, and that the quanta, the nodes, the argument is that where they line up, you can make a photon. So when they're matched, let's just say they're not, we're not talking about making stuff out of pieces. You see, I'm arguing that this whole thing is just made out of pieces, and you're just combining pieces and putting photons together. But even if we just argue about whether they're lined up, and the argument is when they're not lined up, when this is happening, you get no light. So this produces light, okay, this produces no light, when they're out of phase. All right, but how much off it can be is the question. When does it stop making a photon? So can it be a little bit off? Can it be, just a tiny, one tiny little nanometer off? Can it be 5 nanometers off? Can it be 10 nanometers off? And that's what's telling you how big the spot is. So the spot of light that you see is being dictated by really saying this is where they're perfectly in phase. That is, it's perfectly aligned. Okay. And somehow, as you get less and less in phase, that is, if this line starts to curve, bend a little, you can get away with this much bending that way and this much bending, you'd say, that way, and you'll still get something that looks like they're in phase. So they can be a little bit out of phase, a little bit out of phase, a little bit, but there's a certain point where they can't be any more out of phase, and this gets dark. So we're really just saying how out of phase can they be, and they're claiming it's some very gradual thing. Now what you can see in the pattern is that the little spots, the little light spots, really don't have any evidence of going gradually on and then bright, very bright in the middle and then less bright on the outside edges. So there's no real evidence of that, gradually on and then gradually into dark, gradually on. Probably a very good way to draw that that I haven't done, but so the lines would be further apart and they get closer and closer and closer together, and it would get brighter and brighter, and they get weaker and weaker and weaker and weaker and weaker. So we don't see that really gradual on and gradual off thing happening in photons. Now the shape implies some of it, just obviously, if I was to draw a circle, you're going to understand there's less volume of circle here, and there's less volume of circle here, and less volume of circle here, and the most here. So you can sort of get that there's more area in this part here than there is area on this little fringy part here. So they could be illustrating some kind of gradual, but it's not the mechanics that you'd expect it to produce as an image. And it does look an awful lot like an image, like it's the actual laser beam. So I would argue that the reason why some of that happens, the reason why sometimes it looks like little circles or something closer to a laser beam that goes in, the light going in is a circle. And so what can happen is the closer the laser beam is, your source, the closer it is to the slits, okay, the smaller the beam of light, and the more likely it is you might get that the whole beam of light inside of the experiment. And the further away you go, the less likely that is to happen. The more spreading that'll happen, and therefore the surfaces will look your little the things that happen will look squarer and squarer. Okay, the further away you go, and the closer you are, the more you'll get the roundness of the laser beam showing up, and that's why you'll get this stretching shape. That's why you'll get this, shape like this instead of a square bar. All right, that's why you're getting a stretched image, is because of how close or far away the laser beam is to the actual experiment. And it also matters where you put the extra, beam spreading slit in before you get to the experiment. Which is really a way of just saying, I just want parallel light. So if you put it, as much as this will spread the light, what it does more importantly, spread it this way and spread it this way. What it also does, though, is force the light that does get through. A lot of it's going to be parallel now, so it's going very straight. It's not going in at any angles, which will give you a clearer image. Again, a more precise image. All right, so that's the basics of the argument, demonstrating, I think, that light can be understood as, so let me just erase some of this, and we'll just get to some, the argument that waves don't work, okay? I think it can be shown that the math isn't illustrating what they draw, so, they're saying one thing with their math, and they're saying something else with their drawings. So the two of them don't match, and it's just a clear not matching. So just understand the slits this way. Their math is using this distance, okay? Their waves, the point sources would be here. So their math isn't using the real point sources. It's using ones that aren't the real point sources. And for the two-slit math, when they're doing the cheap version of it, they cheat all the way by making the slit infinitesimally small. So they make the slit so small that this surface is essentially the same distance. This distance of where these two things are ends up being almost the same as this distance, which means the two patterns would be the same. So they make the pattern, they make the extra sources irrelevant by making them essentially the same place as the impediment. So that's when they do the real cheap version of describing the experiment. And that's the version where they don't have to worry about the two patterns, because there won't be two patterns because you've put the two surfaces almost in the same place. And if you do it right, like I said, you've got a real problem, because the wave center will not in any way, this drawing won't work. It won't work first, and it won't create the right little size of your nodes, but it also won't work because it won't create the two patterns. It won't create the envelope pattern. It won't create the dead spots here, and then the pattern starts again over here. It won't do that. It doesn't have any way to do that. So the simplistic drawings they give you aren't accurate. It's not the most tested and proven math in the history of mankind, or any of the exaggerations they pile on. All right, so photon, understanding it. So again, the classical drawing is something waving, whatever that would be. They don't explain the length of a photon, so they don't say this is a photon, this much is a photon. They don't give you any indication of what a photon is in terms of its size, and they never describe the fact that the polarization of the photon is thousands of atoms. Okay, thousands, 2,000 atoms worth of polarization. It's gigantic. Okay, so even though the photon is small, the description is way off in terms of really realizing how huge the thing we call a photon is. It's really big in terms of the space it covers, in at least one dimension. Its polarization dimension the photon is very big, okay, really big. And I argue that you can reduce the whole thing to just quanta moving the speed of light. That is little bits of energy, momentum moving the speed of light, all going the same way. And the trick is of their polarization is they were sent at different times, so they occupy a different place in space. So instead of this drawing, you just do this drawing, okay? All right, so this accounts for your frequency this way, and you account for the polarization this way. And that's a photon, and what you can do to that photon is you can wipe out pieces of it, and then you can send pieces of another photon that fill those gaps and recreate your frequency. So you can break the quanta, you can send the quanta in different directions, and the fact is if you do it to 1,000,000 photons, you'll send enough of them going this way to this location from different areas, and they'll all hit here at the same time, and they'll all hit here at the same time, and you'll just remake this pattern. And so you'll just break photons and then remake them. There's no destructive interference, there's just constructive reconstruction of the quanta of the photon. And the number of them just decides, human beings can see 6 quanta, 6 to 9, the number's kind of mushy, and a frog would see 3 to 5 as its minimum. If it doesn't see that many, it can't see the photon either. So that's the difference between, so we know that frogs would see the pattern different than we see the pattern, because it would see rays of light of different sizes. Okay, so the length of the photon is a key. Part of it is its thickness this way, and part of it is its length this way. So I don't know what I did with my little piece of paper, but to use the paper analogy, and the paper analogy is sort of correct, but polarization, that is the going this way, is proportional to the frequency going this way. So the paper is not exactly right, because I say there's a whole bunch of little quanta on that piece of paper. Little bits. But yes, the frequency is proportional. This is proportional to this. All right. But the number obviously would make the photon longer. So my piece of paper analogy would have to be 6 pieces of paper. So the photon occupies a rectangle in space. So this is a photon. Okay. And the truth is, a frog can see a photon that looks like this. Whoops. Yeah, went too far. So frogs see this photon. We see, well, I should make this one bigger because we don't see nearly as well as a frog. But anyway, it has to be this long for us to see it. It has to be this long for a frog to see it. So it'll count more photons, you can see, obviously. And that if there's a stream that's, very long, our brain will just say photon 1, photon 2, photon 3. It'll just break it into clumps big enough to say, I got that one. And then it'll start over again and say, oh, I got that one. And then I got that one. So a ray could be continuous. And we'll just break it into a number of, our brain will just break it into a number of events. Photon, event, electricity, created. 6 of them, electricity created. 6 more, electricity created. 6 more, electricity created. So our brain will just count them as incidents of lightning, let's say. Bolt of lightning, bolt of lightning, bolt of lightning. But it's sort of arbitrary because the ray could be, very long. Yeah, so that's the other thing I wanted to mention. And there was something else. Fundamental, elemental to this whole... Oh yeah, so the other experiments all demonstrate this. So when they do a radar experiment with 2 slits, they have 2 sources of the radar that, are the radio waves. They're connected, so they're always in phase. And the idea is they send out this waves. Well, again, the math for the waves doesn't really work. And the idea that there's going to be this interference. Well, the vector math is exactly the same for jamming. So you could just say the signal's jammed where they're in phase. Okay, when you send 2 signals from 2 different places, I mean, sorry, when they're out of phase. So when they're in phase, they're compatible, the radio signals, but when they're out of phase, that is, the two signals are coming in out of phase, drawn like this, the radio can't tell, what it's receiving. You can't make any sense out of it. So it says nothing's happening, even though it's getting hit by plenty of energy. It's saying I can't resolve it, I can't tune it in. So jamming explains why we can't make a receiver that can see any signal at these locations. So it can make a signal here because they're in phase. It can't make a signal here because they're out of phase. And if they're out of phase, it's a fault of our radio receiver. It's not that there's no energy there. There's just no way to receive the energy because it's two different signals at the same time, and the radio receiver has to be able to tune in to the frequency. It has to duplicate. It has to match the frequency, and it can't match two different frequencies, two out of phase signals. It can't create a resonator to two out of phase signals. It needs to have one be stronger than the other, or that's it. It just needs them to be in. They have to be in phase. If they're out of phase, it won't receive anything. All right. So jamming can explain that experiment, and then the electron one, I would argue, is very bogus in every respect, because unlike the photon, electrons don't have any polarization. So electrons are some sort of, now they say they're a wave, so they give them a frequency, a de Broglie frequency. So even though it's a single object, I guess we're supposed to think that the single object can be understood as a bunch of nodes somehow, a wave. Now I say that's kind of silly, but whatever. But the truth is it doesn't have any known polarization, no thickness in space. It's very tiny, and it's so tiny by its actual size, okay, that we can't make a slit that would be proportional. So when we make a slit in a material for light, the expectation is the polarized light, might be this size. The polarization might be this size compared to the slit, with a very narrow slit. Maybe 3 or 5 or 10 wavelengths could fit in there. So that means 10 or 12 polarizations could fit in. So they'd be very visible. An electron would be 1,000,000 times smaller than that. And so to make a proportionally confining slit, the slit would have to be something like 100 or 1,000 even, right? To make little bars in that double slit, that's probably where there's 2,000 of those little bars making up the whole pattern. So if you go across the whole arc, there'd be 2,000 of them. As an example, the little dots, if you went all the way, both directions, and counted them all, 2,000. You can't do anything comparable to that with an electron. There's no way to just say, okay, I'm going to go 2,000. I'm going to make a slit the size that's 2,000 times the width of an electron. Well, an electron is 10 to the whatever minus some kind of silly number, 23, let's say, meters. It's a tiny thing. So you'd have to make a slit that was smaller than an atom, right? So you understand, to make a slit that's as confining as the slit that the light's going through, you'd have to make a slit that's actually smaller than an atom. A lot smaller than an atom. So obviously there's no logic to this, and so they're using a de Broglie wavelength and saying, and essentially the de Broglie wavelength is saying the momentum of the electron, the power of it is somehow proportional to its frequency. And so, unlike light, so they're saying because the electron's moving fast, it's powerful, and therefore they'll give it a wavelength. And that wavelength will be, yes, it's going to be smaller than, say, an X-ray, but it's still going to be gigantic compared to the reality of the electron, the size of the electron. So they've given the electron a lot of power for a very tiny thing. More power proportional to its size than the photon. So the photon is really big and kind of weak. The electron is tiny and very strong. So by their equation where they say frequency equals momentum, and vice versa, momentum equals a frequency, they've given the electron a very, very, much bigger size than its actual size. And so they can, construct a two-slit experiment by those standards that might be, but it's still going to be way out of proportion to something we can reliably build. So building a two-slit for an electron is really difficult. So first I'd argue it's impossible because you have to make your structure out of things smaller than an atom. And the second argument I make is electrons are charged for, they're charged. Unlike a photon, they have a charge. And how can I pass them by any surface that I know is covered in electrons and protons, that's covered in charges, without expecting the electron to do all kinds of wacky crap? And the very fact that electrons are charged means that when they're traveling through space, they're going to end up moving, away from each other. So if two of them start off this way, as they travel through space, they're going to move away from each other because they don't like each other. And then they're going to end up banging into each other's force, so to speak. And so like the iron filings around a magnet, they're going to end up in a pattern. So they don't have to travel very far before they're going to end up in lines, because they're going to be trying to avoid each other. And the more they travel through space, those lines are going to diverge, obviously. So obviously you're going to take electrons that'll start off in all kinds of places. All right. And, I'll just try to do a random thing with electrons. They move a little bit of distance, and in that time, they're going to start segregating. So they're going to segregate into lines. And then, as they move a little more distance, those lines are going to separate, obviously, because the electrons hate each other. So, yes, obviously, you would expect a pattern. Yeah. So I'm just saying all the corroborating evidence is loopholey and thin and, unconvincing when you really analyze it, as is the single slit and the double slit. This evidence is not evidence of waves, it's evidence of momentum traveling straight lines. It's evidence of rays, and I would argue rays of particles. So and again, I'd say particles just because ethers are just unnecessary. So one could argue that the momentum is just traveling through a bunch of dominoes. You're just flipping dominoes, domino, 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 domino. Okay, and so the whole universe is made of these dominoes, and you're just pushing dominoes. This domino pushes into that domino pushes into that domino, blah, 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 blah. And that's what light's doing. It's pushing a bunch of dominoes. But the simple explanation is hell with all that. Just make dominoes that you can throw. Okay, so I don't need all these dominoes if I throw the domino. So just having this bit throwable solves all the problems. Because this is the problem with arranging a bunch of dominoes is there's no geometry you can create. The checkerboard breaks down because the diagonal distances on a checkerboard end up being longer. Okay, you can sort of understand. This line ends up being a lot longer than this line. So the geometry of your domino system breaks down because then this direction ends up being a lot more than this direction. And you can't have that kind of brokenness in your system because we don't see any evidence of that happening. We see evidence that every line, every direction is exactly the same time, the same distance, the same everything. So an ether really won't work. But anyway, don't need to make that argument. But it's part of what underlies all this, because waves in jello make sense to people, and I'm just trying to say, no, it's not waves in jello. Even if it were waves in jello, the jello would have to have pieces in it that push on each other. So that all breaks down anyway, and it's just simpler to just say there's stuff that's moving the speed of light forever, and it can bang into something called a matter bit, and while it bangs into it, it moves it. And then it stops moving, and then something else bangs into it, and it moves, and then it stops moving, and then something else bangs into it, and it moves. And that's a simpler explanation. So anyway, that'll be something like what will be under debate when we get there. That argument is going to be made, and it's going to be made that this is a huge cornerstone of all of quantum theory, and it's styrofoam. It's a crappy cornerstone. It's just sand falling apart. It's not cement. It's not made out of any kind of hard material. It's very soft, very easy to break, very easy to find the flaws in it, and they're really overt. Like I said, the flat screen projection was, any physicist should know that's not going to work. You're going to get a whole bunch of distortion. You have to view it on the proportional screen, proportional distance screen, to see it for what it really is. And when you do that, you realize there's no infinite patterns, there's no mystery to it. All these nodes have to be the same size because the wavelength difference is always the same amount of distance. So, you know, there's just no way of getting around how simple it becomes. And it's about things moving in straight lines. And there's no curved lines anywhere that aren't made out of straight lines. Alright. That should be, good practice anyway, and such. So, till the next time, and such. I think that's all I need to say in this video. Yeah. It's probably not, there's probably something you should have included that. But I can't do everything. Just can't keep track of everything. Too many quanta bouncing around in my world.